Hello everyone. So today let's solve the problem ST spanning tree. So this was asked in the code forces around 375 for the division. Let's see what the question states here. You can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. Right. So let's see what the question states here. So we are given an undirected connected graph. Right. So we have been given undirected connected graph. Right. So with the n vertices and m edges with n vertices and m edges, right? And we have been given two special vertices s and t with a this one degree limits ds and dt. We have been given two special vertices, this one s and t with degrees, s and t with a degree limit, sorry, with a degree limits ds and dt, right? So we have been given two special vertices s and t with a degree limit ds and dt respectively, right? So what we need to do here, we have to build any spanning tree. We have to build here any spanning tree. We have to build any spanning tree with a n minus 1 edges here, that is connected, whose degree at s less than or equal to, whose degree at s less than or equal to ds and t less than or equal to dt, and t less than or equal to dt, right? Or we have to print no if it is impossible, or we have to print no if it is impossible, right? So we have to output any valid spanning tree edges if it exists. What we need to do, we have to output any valid, let me write it over here, output any valid. So we can have the multiple outputs, right? So they have asked us to go with any valid, this one spanning tree edges, basically spanning tree edges, right? So if it exists, right? So this is fine. So this is the question they have asked. Let me read the question out loud. Just listen to this carefully. So we have been given undirected connected graph with the n vertices and m edges, right? And we have been given two special vertices s and t with the degree limits ds and dt, right? So this is fine. Now we have to build any spanning tree n minus 1 edges connected, basically whose degree s is less than or equivalent to this one ds and t less than or equivalent to the dt, right? Or we have to print no if it is impossible. We have to print no if it is impossible. Then what we need to output, uh, we have to output any valid spanning tree edges if it exists. We have to output any valid spanning tree edges if it exists, right? So this is the question basically. Now, yeah. Now, as we have the understanding of the question, let's do one thing. Let's discuss the approach followed by the complexities, and then let's write the code. As usual, let's discuss the approach first. Just give me a second here. Yeah. The first thing here would be, so we will be making use of the disjoint set union, right? So we'll be making use of the disjoint set union for the path compression, or we'll be going with the union find. Both are same, right? So we'll be going with a union find to solve this particular problem. So recently we have discussed the union find algorithm as well, right? So we have the idea on the DSU or the union find. So very recently, right? So this is fine. Now, first step, what we will be doing here, we will classify each edge, whatever the edge, we will be classify each edge by how many endpoints are special, right? So by how many endpoints are special, we'll classify each edge by how many endpoints are special. How many endpoints are special? When I say special, we can just consider S or T, right? So this is fine. So edges touching none, one or both. So this is edges touching one, none or both, right? So this is fine. This is the first point. Then the second point would be, we will be making use of the disjoint set union to greedily add edges that do not touch S or T first, right? To greedily, this one, add the edges, right? To greedily add edges to uh, do not touch S or T, to do not touch S or T, basically. This is the second point, right? So this, what it does here is, this connects as many components as possible without consuming ds bar dt, right? So without consuming ds bar dt. So this is important one. Yeah, let's move on with the next point here. So the next point here would be, next we will be adding the edges that touch exactly one special vertex. What we'll be doing, we'll be adding the edges that touch exactly one special vertex, right? One special vertex if they connect different components and degree budget allows, right? So we will be basically adding edges here that what it does, that touches exactly one special vertex, one special vertex, right? So this is fine. I'll just write here one special vertex. This is fine, man. Now let's move on with the fourth point. So this fourth point here, this one, what do we call? Finally, what we need to do, we have to consider the edges that touch both S and T, right? So we have to consider the edge that touch both S and T, that touches both S and T, right? So here, yeah, we can then use the remaining budgets DS and DT to add it if only this one, if required to connect the final components. So this is fine. In the example, after adding 2 to 3 and 1 to 3, in the example, after adding 2 to 3 and 1 to 3, right? In the example, after adding 2 to 3 and 1 to 3, we already have the spanning tree edges, right? The spanning tree edges are uh, this one. In the input itself they have given, you can just check. So the spanning tree edges are 2 comma 3 and 1 comma 3. We have considered the first example for the approach, man. Yeah, you can just look into the first input or the first example. In the example, the first example, after adding 2 to 3, this one edge 2 to 3 and then 1 to 3, we already have the spanning tree edges 2 to 3 and 1 to 3. The first example we have considered, and both ds dt budgets are respected here. So S used this one 1 and T used 0. S used 1 and T used 0 here. T used 0, right? So if we can collect exactly n minus 1 edges under the budget, then we have to print S, right? And the edges. Otherwise, we have to print no. In our case, we have to print S, right? So we can collect exactly n minus 1 edges here. We have to print S along with the edges, right? So we can just go with the 3, 1 and 2, 3, right? 1 3, and we can just go with the 3 2 and 1 3. It doesn't matter, this one order doesn't matter. We can just go with the 3 1 and 2 3 or 3 2, right? So these edges, so undirected graph, right? So we can either go with this one 3 1 2 3, or this one 1 3, or this one 3 2 as well, or we can just go with 3 1 3 2, those combinations. That is fine. As this is undirected graph, man, all we have to go with is 3 1 or 1 3 edge and 2 3 or 3 2 edge, right? So I hope this is fine, right? So see here, we have been given n and m. Then the output that we need to get here is this one, 3 1 and 2 3. See here, the same thing as I've said. Order doesn't matter here. 1 3 or 3 1, 3 2 or the 2 3, right? Order doesn't matter here, right? So this is fine. If there are several this one solutions, print any of them, right? So we can just print any of them. This is fine. So yeah, this is about the question. This is about the approach. Basically, we have successfully discussed the question, input, output, as well as the approach, right? Now, as we are completely familiar with the approach, let's discuss the this one, complexities part. So now we saw how we got the output. This one is 3 2 and 1 3 edges, right? So this is fine. Now, what is the time complexity and the space complexity actually? The time complexity and the space complexity. First, let's discuss the time complexity. The time complexity would lead to pico of m log m plus pico of n into m, right? So this is the time complexity. What would be the space complexity? The space complexity would lead to pico of n plus m, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be pico of m log m plus pico of n into m and pico of n plus m respectively, right? So this is the time complexity and the space complexity. So as we are completely familiar with the approach and the complexities, let's do one thing. Let's start writing the code, right? So just give me a second here. Yeah. Now, first we'll be making use of the fast input and output. So let's import input output package, man. Yep. Also, we'll be making use of the different utilities. I'll just import util package. So this is fine. Now let's move on with the this one class. Let's go with the class. Create the class actually. Main as usual. You can just give any class name that's related to the question that's relevant with the question basically, right? So we have to go with the edge as well as the we will be going with the helper method find as we are making use of the DSU, disjoint set union. Usually we'll be going with a find and union, right? Find to find the representative to X and Y. In general, I am speaking. If you don't know the algo, disjoint set union, you can just watch the algorithm and come here, right? So recently we had discussed the disjoint set union algo. So that's very easy, man. Find method, what it does, it finds the representative, also known as the parent, right? So union, what it does, um, union basically we will be going with a path compression along with the union by ranking, right? So we have to eliminate the taller ones, right? So we will be eliminating the taller ones. We will be going with a union by rank in general terms I'm saying, right? So this is fine, I believe. So let me copy paste as we'll be going with the class edge and we'll be going with the helper method find. Just give me a second here. So let me come here. So within the main class, so this is nothing but the edge. So what is this edge class basically? This stores the two endpoints. We have to store the two endpoints u and b, right? Also, we have to go with the z. Number of endpoints has to be equal to s or t. That's what they have given in the question. So we are going with a u, v, z here, and this is nothing but the initialization part, also known as constructor part, right? Constructor assigns the endpoints here, u, v, as well as the z. So this one is parent. So this is nothing but the DSU parent array. So here within the find, we will be finding the representative or the parent itself, right? So this is the parent variable, DSU parent array. If you know the this one DSU algorithm. So what we will be doing within the find this one method. So find method or the function, whatever we have written here. So this one comes with a path compression actually. So sorry. Previously I had said that we'll be going with a path compression within the union, right? So within the union, we'll be going with a this one union by rank actually, right? We'll be removing the taller ones as I've said, taller subtrees, right? So sorry, this one the path compression we'll be doing within the find, yeah. So sorry for that. This is fine. So within the find function or the find method with the path compression, um, so we will be returning the representative or parent or root of the X. This we know. So if you know the algorithm of the DSU, right? So next, let's move on with the further things. Now, let me go with the main method, right? So this is fine. Let me give here throws input output exception. So this is fine. So now within the main method, let's do one thing. Yeah, let me copy paste the this one. What do we call? Uh, mm, what do we call? This one buffered input print writer. So the something all the things that are related to the this one input output. Just give me a second here. So I'll just come here. Let me copy paste the things that are related to the input output. So this is buffered reader and the print writer here. So this is nothing but the fast input at the output setup. We know this. So this string tokenizer, whatever we have made use of, this is also this is just to read the first line one. So we have n vertices and m edges here, n and m, right? So this one, and a thing. So three vertices and three edges. So we have to read that. So we'll be making use of the string tokenizer here. N and M is nothing but the numbers 3 and 3. We have to parse them. They are of the type integers, right? So this is fine. This edge, this is nothing but the array to hold all the edges. We have to store this one. We have to have something to hold the edges, right? So this is nothing but the array to hold the all the edges. Now here, this for loop, we are reading all the m edges here, right? So we are reading all the m edges. Simple. This is completely related to the input output. Then we have to read the last line, special vertices and their degree limits. One more thing here, the original code uses the variables k and t and this one for the s and t basically. In place of s and t, we are making use of the k and t, right? This is fine. So we are going with the k and t. Don't get confused here, right? So in the approach, I discussed with the variable names s and t. In place of s, we are going with the k. That's it, right? So this is fine, man. Now let's do one thing. Mm, yeah. So I'll just go with here. Next, let's move on with the main logic. So here for every edge, we have to compute z. When I say for every edge compute z, So we have to see how many endpoints are equivalent to the K or T, KRT, right? So we'll be going with a 0, 1, 2. So I'll just go with for edge E of edges. So this is fine. So within the for loop, what we'll be doing? E dot C equivalent to E dot U here. So if it is equivalent to the K or E dot U here, it is equivalent to the T, then what we'll be doing? 1 else 0, right? So this is fine. Along with it, let me go with E dot V here. This is fine. If it is equivalent to the K, if it is equivalent to the K or E dot V here, if it is equivalent to the T, then what we need to do? We have to print 1, else we have to print 0, right? So we are just going with the ternary operator here. This is fine. Now let me come out of this for loop entirely. Now let's go with a random shuffle. When I say this one, random shuffle, this one. So this code has to produce the varied ordering before the stable sort, right? So that is the reason we'll be going with a random, this one shuffle here. So let's do one thing. How can I write it in the form of code? So I'll just go with here random and here new call random. So this is fine. So next, let's go with a for loop here. This one int I equals m minus 1 I greater than 0. Let me go with I minus minus. So within the for loop, what we will do, let's assign the j. Let's assign the j to this one read dot next int here. So this one I plus 1. This is fine. Next, let's consider the temporary variable tmp here. So this one has to be edges of I. So this is fine. Also edges of I. So this is equivalent to the edges of j. So this is equivalent to the edges of j. So this is equivalent to the temporary variable. So this is fine. So let me come out of this one. So now let's do one thing. Let's sort the edges by z, right? In the ascending order, right? Edges with 0 first, then comes L, then comes the set. So let's sort here. So I'll just go with arrays dot sort. So this one, let me pass edges along with a comparator. Sorry, along with a comparator. Dot, so this one will be comparing int. So this one will be comparing int of a this one to set. So this is fine, man. Now let's do one thing. Let's initialize the DSU parent array, man. Disjoint set union parent array. Each node is its own parent initially, right? So I'll just go with parent equals new. This one will be new int of n plus 1. So this is fine. So let me go with a simple for loop here. Int I equals 1. This is fine. I less than or equal to n. I plus plus. So this one parent of I. So this is equivalent to the I. This is fine. Now let's go with one more thing here. Let's go with a list to store the chosen spanning tree edges. So this one will be list of the edge. So this is fine. List of edge. So let me go with the answer variable or the result variable here. So new, let me go with array list here. Let me complete the syntax. This is just the list to store the chosen spanning tree edges. Now we have to go with a greedy approach, or so we'll be making use of the greedy pass here. Greedy pass in the sense we will try to add the edges in the increasing Z or Z order while respecting degree budgets, right? So that's what we need to do. That's what we discussed in the approach as well, right? Let's try to do the same here. So let me go with a for loop. So this one for edge E of edges. Yeah, within the for loop, let me go with the root of u and root of v. So this one as int x equals find of e dot v. This is fine. E dot first and in y equals, so this one find of E dot y. So this is fine. Now we have to check whether this particular edge touch the k or not first, right? We had considered the variable s in place of k within the approach. Don't get confused here. We have to check whether this particular edge touch k and touch t. For both this one we have to check actually. For the I'll just go with this one variables tk and tt. So first let's check whether this particular edge touch the k or not. So this one e dot u, if it is equivalent to the k, or e dot v, if it is equivalent to the k, then display 1, else display 0, right? So this is fine, man. Yeah, so let me go with the same thing with the tt as well. So I'll just go with here, uh, instead of k, let me go with t. This is fine. E of u equals, we are checking for t here in this case, right? Again, we'll be checking with t along with the v, e dot v. If it is equivalent, then we have to print 1 else 0, the same thing, right? So this is fine. We have successfully checked whether this particular edge touches k or t, right? So this is fine. Now what we will do, we have to skip if u and v are already connected, right? So that's what we need to do. So for that, let's write the simple if condition. If x equals y values, or dk here less than tk, right? Or even one more thing, what if dt less than dt? Then we have to skip in that case. Let me make use of the continue keyword here. This is fine. Yep. Now let's merge the two components in the this one disjoint set union. So how to merge? So let's consider the parent of x we have to consider, right? We have x and y, sorry. So we have to assign this one to the y. This is how we merge basically. And finally, after merging the two components in the DSU, we have to add this particular edge to the answer variable. We have considered a and s. So let me go with add. Add what we need to add here, edge, right? E. This is fine. Next, we have to deduct the budgets accordingly. So we have considered variables dk and dt for that. So this one we are deducting, right? So dk equals dk minus tk, right? This is fine. And dt equals dt minus tt, dt minus tt. So this is fine. Next, let me come out of this one entirely. Now, after processing, if we couldn't pick n minus 1 edges, it's impossible, right? It's impossible under current greedy choices, under current greedy choices, right? So this is fine. Let's go with a simple if condition. So this is fine. Just give me a second here. So let me go with a simple if condition here. If answer dot size, if it is less than n minus 1, then let's print here no. So this is fine. Yeah. else else what we need to do, let's go with out dot println. So this one we have to print s. We have to print s. So also we need to do one more thing. So we have to print each chosen edge as well. Right. So this one s is fine. Then we have to print each chosen edge as well. 3 2 and 1 3. This one also we have to do, right. So for that, let's go with a for loop here. For sorry, capital edge e of answer that we got here. So I'll just give here out dot println. So this one we have to print the chosen edges, right? So this one e dot u plus we have to leave the space here. 3 space 2, 1 space 3, right? Place plus also we have to go with u dot v, edges u and v, right? From u to v. Sorry. We are just printing the each chosen edge here. Fine. This is fine, man. Now let's do one thing. Let's ensure all the output that is written. I'll just go with out dot flush here. Out dot flush. This is fine. So yeah. So this is it for the code. You can just go with out dot flush or out dot. This one close. Both either of them works. So this is it for the code. Before checking the code with the different inputs or the examples, so let me copy paste the signature starter template. Just give me a second here. So I'll just come here. Let me paste this one over here. So I'll just come to the question. Let me copy this. So let me paste it over here. So let me run this. We have cannot find the symbol. Read dot next line number 59. Where is it? 59, 59, 59. So random R&D we are going with. This is fine. So just give me a second here. 1 second. So yeah, but we have considered this one variable RAND here. So I have given the read here. So this doesn't work. So we have to make use of this variable, right? So let me run this one again. So many errors are gone now. Cannot find the symbol. So this C has to be small one. Line number 65. Line number 65. We are going with a what do we call comparator? This one, but comparing it. So this C has to be small again. This is fine. This error has to be gone now. Yeah, we are left with only one error. Cannot find the symbol E dot Y. Into Y equals find of E dot Y. Line number 74. What happened here? Why this is showing error? I'm not getting. So yeah, so I have given this variable here, man. So we are going with the edges U and V, right? So here we have to give the edge basically. This has to be B. Yeah. Now let me run this one. Yep, we are getting the correct output. Yes, 3, 1 and 2, 3. Right. So here 3, 1 and 2, 3 here in the sense this is undirected graph. So it can be of any order basically, right? So this one, this edge we are getting up actually. Instead of 1, 3, we are getting 3, 1. Order doesn't matter as it is undirected graph. And 3, 2, instead of 3, 2, we are getting 2, 3 as it is undirected graph. So this is also fine, right? So this works absolutely correct. So this is also fine. Next, let me go with this one. Yeah, the output that we need to get here is, yeah, yes, followed by 1, 2, 1, 3, 5, 7. 1, 2 we have, yeah, 1, 2, 1, 3. So this is also one of the valid answers. They have asked us to see here if there are several solutions, print any of them. So this is one of the correct solutions as well, right? So this also works accordingly with the code that we have written. This has to work. Let's see. So now let me copy the code. Let me come here. Let me hit the submit button. So let me paste the code over here and hit the submit button. Right. So let's wait for some time. Let's wait for some time. I hope this works for all the test cases. Let's see. Yeah, running on test 22. Yep. We are getting the wrong test on 68. Let's check what is wrong here. So there was a typo actually basically here within the rhyme. So this I have changed actually a bit, right? So this is fine. This one actually, this part actually, this is fine here as well. One or two typos I have fixed that one. So here the output, now we are getting the output as little bit different. 1, 2, 3 to here. We were getting the wrong output for the second input basically. So that is the reason it was getting failed actually. Let me do one thing. Let me copy the entire code again. So I'll just come here. So what shall I do? 1 second. Let me hit the submit button here. me paste this one over here and hit the submit button. Let's see whether this works or not. I hope this works for all the test cases. Let's see. I thought that would work, man, still. Anyways, let's see whether this works or not. Let's see. One mistake would cost you a lot of this thing, man, time basically. Yeah, yeah, you can clearly see here. And the verdict that we are getting accepted, right? So we have made use of pure this one disjoint set union here, or the union find basically. We are going with the find helper method or the find function right here. So this one we have made use of the DSU to solve this particular problem, disjoint set union, the path compression one basically, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.